Learning and explaining how to derive an equation is never much fun. However, the kinetic theory of gases gives rise to several important equations, and most examination boards in advanced level physics require you to understand this and the assumptions on which it's based, but, by the way, I'll emphasize, not really to learn by rote. Anyway, let's start. Suppose we get a box and then trap inside it just one particle of gas. Just one molecule, which with our X-ray eyes we can see. And by chance it is bouncing backwards and forwards between a pair of faces, going in just one direction and back again. In doing that, it bounces off, it rebounds from the opposite pair of faces at the end of the box. In the initial direction, it has a momentum mv, where m is the mass of the molecule and v is its velocity. On rebounding from the box, the momentum reverses because the velocity reverses. So it has a new momentum mv, but in the opposite direction, so we have to call that minus mv. We are assuming here that the collision is perfectly elastic. There is no loss of energy. But that seems a reasonable assumption. If we trap a box of air, for example, and come back to it after a while, it looks much the same. The molecules don't all lie then at the bottom of the box. So using this assumption, we have a total change of momentum of mv in one direction to mv in the other direction, which is a total change of 2mv. Now the second step is to find how long it will be between collisions. If the length of the box is L, then before it hits that face again, it will have to travel a distance 2L. Yep, that's right, the molecule has to go 2L. And at a speed of v will give it a time taken to go there and back of 2L over v. That's distance divided by speed. And in doing this little calculation, we make another assumption, that the actual distance travelled is 2L, and that means we have to neglect the size of the molecules to say that is insignificant. We can use these two little expressions we've derived to create another expression, which is the average force on the face of the box. Now, force is change of momentum divided by time. The change of momentum on one strike is 2mv, and the time between one strike and the next is 2L divided by v. So the division gives us 2mv divided by 2L divided by v. The 2's cancel out, the v will go to the top, so it's mv squared divided by L. Now one step further. We'll imaginatively call the width of the box W and the height h, and so the area of that face is WH. And so the average pressure on that face will be mv squared divided by L, all divided by WH, the area. And that will give us mv squared divided by LWH. But LWH is the volume of the box. So we can simplify this expression down to mv squared divided by big V, and big V is the volume of the box. Now we've only considered one molecule, but in a real box there'll be lots of molecules. Let's call that number n. But by chance, all of these molecules are bouncing backwards and forwards, in this case horizontally along the box between the same two faces. If all of these molecules have the same mass, then the force on that face and the pressure on that face is going to be n times as much. That is n mv squared over big V. But, of course, as I'm sure you've thought to yourself already, that's a bit silly. These molecules will be flying all over the place, going up and down and backwards and forwards and sideways and diagonally, every possible direction. They're travelling in 3 dimensions, so they'll be hitting 3 pairs of faces. So the expression we derive for the pressure on one face will now be nm v squared over big V, all divided by 3, which simplified is simply nmv squared over 3v. So in examining what we've said in deriving this expression, pressure is nm little v squared over 3 big V, we've made a few important assumptions. We've assumed that the pressure on each face is going to be fairly constant, and for that we're assuming that must be a very large number of molecules. So the time between the individual impacts is tiny. We've assumed that the motion of the molecules is entirely random, striking each part of each surface equally often. And finally, we're assuming that there are no other forces between the molecules which will disturb this linear motion that we've been talking about, except, of course, a force at the instant of collision. Now, just a final couple of steps before we extract something which is fairly useful. The first one is to get round a bit of an algebraic problem. As we've said, all these molecules are going in different directions. For every one going up, there'll be one going down. For every one left, there'll be one right, and so on. And velocity is a vector. And so if we take an average velocity, that's going to be 0. And that's going to make a nonsense of our expression. So what we do is we use what is called the root mean square velocity, the RMS velocity. And that is created by squaring every value, so they'll all be positive, finding the average, and then taking the square root. The final value that we get is much the same as the average speed. This is a device. The symbol for the RMS value is C with a line above it, bar C. So now the equation becomes pressure is Nm bar C squared over 3V. Now a useful way of rearranging this is to separate out Nm over V. N's the number of molecules and m is the mass of each one. So Nm is the total mass. V is the volume. It follows there, mass over volume is density. And finally, our equation becomes pressure equals density times C bar squared over 3. Adding just a minute or so to this video, I'll just show you a typical examination question using this equation. You're given the density and pressure of a gas and asked to find the average speed of the molecules. Using our just derived equation, from this we get 101,325 Pascal is equal to 1.25 bar C squared divided by 3. We rearrange this to get an expression for bar C squared. Using my rather ancient and not particularly scientific calculator, we punch in the numbers and get the expression for bar C squared. But it is bar C we want, so we need to take the square root of that final answer to get our speed of just over 493 meters per second. Thank you for watching.